And we talked about like if the molecular or empirical formula is unknown, it can be derived. And the way we derive it is by looking at the masses of each element. And there are um, instruments that are able to do that. You can take a compound and subject it to a mass analysis, and it'll give you the percentages or the masses of each atom, the carbons, the hydrogens, nitrogens, whatever. Uh, and so that's quite doable. So even if you have a compound that you don't know the formula for, you can derive it. Like you could take it and do what's called a high res mass spec, where you take it and inject it into a mass spectrometer, and you can get the masses out of each atom. So we started out with this simple example. We said we have a 12.04 gram sample of that contains 7.34 grams of carbon. Notice that the masses have to add up to the mass of the sample. 7.34 grams of carbon, and then 1.85 grams of hydrogen, 2.85 grams of nitrogen. And the way you calculate the percent composition, which is what this problem is dealing with, this example, is simply taking the part over the whole. It's like a fraction. You take 7.34 and divide it by the whole mass, which is 12.04, multiplied by 100. And so in doing that, that's how we're able to do, that's the most basic fundamental method for calculating percent composition. There's some other more complicated methods that we'll look at shortly. But yeah, for the most part, this is this is percent composition in a nutshell. So if we take that top number, 7.34 divided by 12.04 times 100 is 60 point, we'll say 61%. We'll see what the other ones add up to. So this is 61%. And then we do 1.85 divided by 12.04. This is 15, we can round down 15%. So the last one will have to be 24%, right? At least, because 15 is 61 is 76. So let's see, we get 2.85 divided by 12.04. Yep, 24%. Right, because it's got a total up to 100%. All right, so when we're doing percent composition like this, if you have the masses of each element and you have a total mass for the sample, you just divide, again, the part by the whole, right? So we can look at another way to approach this percent composition is by let's say this is method B. If we have a known formula, right? If we have a known formula, then we can look at the molar mass and the atomic mass and use that to find the percent composition, even if we don't have the masses. So we can take atomic mass of the element and divide that by the molar mass of the compound. And we're going to show you with an example. And again, it's the same idea. It's a fraction. It's the part over the whole. So we have something like aspirin, which looks like this. Don't worry about the structure. I'm organic by training, so I have to, this is for my own sanity. So, but you'll get when we start talking more about different compounds, then you'll get, you'll be able to draw these yourself with no issue. That's why I kind of sneak it in, because I want to expose you to it now, kind of like that polymer extra credit example where I had you draw out melamine That's on purpose because eventually you want to be able to draw out these skeletal forms. And you know, every place in this molecule, this is carbon, that's a carbon, that's a carbon. Everything that's not labeled as another atom is a carbon, right? So the molecular weight or the molar mass for aspirin is 180.16 grams per mole, right? And the formula is C9H8O3. Oh, not O3, O4. All right, C9H8O4. All right. And so this is giving us like, okay, so we know the atoms. Let's count them up. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. We have for hydrogen, let me show you those. We got a hydrogen here and 3 here, that's 4. And then I'm gonna write them in on the ring. That's 5, 6, 7, 8. All right, and then for oxygen, you can see that there are 4 oxygens right here. 1, 2, 3, 4. All right. So now, if we have a scenario like this where we have the molecular formula and we have the molecular weight, what we can do is figure out the mass of each one of those atoms without actually having it. We can calculate it. So we take the atomic mass of carbon and divide that by the total molar mass of the compound, we can get the mass or the mass percentage of carbon. So let me show you that. So let's take the carbon. We're going to say that we got 9 carbons. So this is going to be 9 times 12.01 grams per mole divided by 180.16 grams per mole, right? And the grams per mole is going to cancel. So 9 times 12.01, what is that? 108.09. All right. Following? Yes, no? Right. And the 9 right here is based on the 9 in the formula, right? So we know that there are 9 carbons. Right. We do the same thing for hydrogen. 1, I'm sorry, not 1, 8 times 1.008. This is carbon. This is hydrogen. 1 times 1.008 grams per mole. I want to put 1 here. Divided by the total molar mass. So we have the molar mass and we have a formula. We can figure out the percentages of each one of those atoms that's in that particular compound, right? So this is all right. So 8 times 1 point is that 8.064. Is that right? All right, and that's going to be divided by 180.16. And then, of course, we'll multiply each one by 100. And so for oxygen, it's going to be 4 times 16.0 grams per mole divided by the total. So for this particular example, we're taking, if we know the formula, but we don't know like the necessarily know the masses of each of the elements in the formula, we can still figure out the percent composition because we can use the molecular formula, the atomic mass of each atom, and then the molar mass, so the total molar mass. We can figure that out. All right. So now we got 4 times 64 divided by 180.16. So let's do these calculations right quick. Somebody take the first one, and then somebody take the second one and the third one, see what we get. And it should add up to 100%. So this is, each one of these is going to be times 100.
The first one, 59.9 or just 60. I don't really know.
All right, let's keep that as, let's make it 60. All right, go ahead with the second one if you got it.
For the second one, 4.47 after multiplying it by 100.
So we're going to say 4.5%. And then go ahead with the third one.
That one just 35.5.
35.5%. So the total should be 100%. So again, this is another way to think about percent composition. If we have the molecular formula and we know the molar mass of the compound, which we can calculate anyway if we have the molecular formula, if we know the molar mass and have the molecular formula, we can figure out the percentages of each one of those atoms in that molecule, right? By taking, again, the molar mass or the atomic mass of the atom times whatever subscript is there, and then divide that by the total molar mass of the compound. So this is the formula for that. So it'll be the atomic mass of the element divided by the molar mass of the compound. And that's how you can find the percent composition based on those two terms, right? First, in the first example, we had a mass of a sample, and then we had the masses of the elements, and we did the same thing. It was just part over whole, right? It's the same thing here. Only difference is we have the atomic masses and the molar mass. So it's still, but the concept is still the same. The percent composition is the part divided by the whole times 100. All right. Any questions about that?
Can you go back up a
Oh, yeah.
little? Get this. There we go.
All right, we're going to do another example like this just to kind of reinforce it. All right. Let's take iron 3 oxide. Which is Fe2O3. All right, what is the molar mass of this compound? What's the molecular weight? Molar mass, molecular weight. How do we calculate that?
By taking the atomic weight and multiplying it by the subscripts.
Yes, so the atomic mass of each element times whatever the subscript is. Good. So for iron, it's going to be what? 2 times 55.845. I think that's what's on the periodic table. Let me get a better pen than that. And then for oxygen, is going to be what? 3 times 16. I always just round that up to 16. All right. So then we got 111.69 for that. And then for this one, 48. And then if we just sum them up, that's going to give us the molar mass for that compound, right? Which is one, it's going to be 159.69. Everybody okay with that? And this is in grams per mole. So I know my molar mass, I know my whole. Is that right? And now I just need to focus on the parts. So for iron, it's going to be what? It's going to be this same number right here. Two times 55, and this is for Fe. Divided by 159.69 times 100. And then for oxygen, it's going to be this number right here, same thing. I know I just cheated, but it's Friday. All right, so that divided by what? 159.69 times 100. Again, it's the part over the whole. Right? If you have a molecular formula and you want to figure out the percent composition, you just take the part over the whole. All right, can somebody hit these two calculations real quick?
It's 70-30.
70% here, 30% here. Excellent. All right. So again, there are multiple ways to approach percent composition. You can approach it from a mass perspective, where you have the masses of each element and the total mass of a sample. You can approach it from the molecular weight perspective, where you have a formula and you have to determine what percentage of that formula each element represents, which we've just done. And then there's another way to do this as well that we're going to look at. And it is, there's a similar way to do it, but that's going to be when we determine the empirical formula. So we're going to use all this information that we have here to set up calculations to determine empirical formula. But let's move to that. So let's go to empirical formula and let's just start talking about that. Any questions about this before we move forward?
And it's just a quick question.
Yeah, go ahead.
Did you have something like similar to this on the test?
No, it was so this is, I'll put it like this. When you're doing those calculations for constant proportions, it's very similar to this, but it's not the same thing.
Yeah, because it was this question I remembered. It was something like it had like 47 grams of sodium.
Yep, sodium bromide.
Yeah.
You have to figure out how much bromine was there.
Yeah, I got real confused.
Yeah, so when you have and it's, again, there are a lot of similarities between this and the law of constant proportion. That's what all this stuff is based on. The law of constant proportions and multiple proportions. Like when we look at, especially when we start talking about empirical formulas, it's going to be basically the same thing we talked about with multiple proportions, how atoms combine in small whole number ratios for different compounds. So yeah, it is similar, but it's not quite the same. So like with that example on the exam, right, you have 47 grams of sodium bromide, and then you had to figure out how much of that was bromine if X amount of grams was sodium. So taking the ratio of the atomic masses, that's very similar, but then you just take the ratio and multiply it by the total mass. So in a sense, it is similar. The setup is similar, but it's not quite the same. Yeah. So the way you would set that up, and I'll just write it over here in the corner. So you had 47 grams of a sample of NaBr. And let's just say, for the sake of argument, that 30 grams of that is sodium. You got to have one or the other so you can figure out the second one. And then what you would do is just take that 30 grams and convert it into bromine using the atomic masses. So this is 79.9 divided by, I think sodium is, what is sodium? Is it 29 or 21? Somebody look at the periodic table real quick. Tell me what the atomic mass of sodium is.
23 if you round it.
23. So the grams of sodium are going to cancel. So if you have 30 grams of sodium, this is the same as setting up a conversion between sodium and bromine, but you do it using the atomic masses. And if there's a subscript, then you have to take that into account in that calculation too, right? But that's for constant proportions. But you'll notice that I'm glad you said that too, because I was thinking that as I was prepping the lecture, like this is all based on constant proportions and multiple proportions. It's the same ideas. It's just applied to a different concept. All right, but this is let me erase that, or should I leave it? I'll just label it. I'll label it as a review. But yeah, the setups are very similar. So that's a great observation on your part. All right. All right, let's shift gears. We're going to now move into talking about empirical formulas. And again, a lot of this stuff a lot of these calculations are going to be similar, because what we're really doing in determining the empirical formula is finding the mole to mole ratio of each element in a compound. Right. So this is the same chapter, new concept. So this would be I guess 3.2 C or B. We're gonna label it. Now I'm gonna take that empirical formula and abbreviate it so I don't have to keep writing it out. I'm just gonna you'll see me abbreviate it as EF. All right. And really what this is, the empirical formula is finding the mole to mole ratio of elements. All right. So when we do that, what do we need in order to find moles? Based on what we've already done, what are we going to need? Remember that grams over moles equals what? Molar mass. So by default, grams over molar mass equals moles, right? So we're going to need this. We're going to need grams and molar mass in order to find moles. So all these calculations are going to involve either a mass already given to you, or it's going to involve you finding the mass or determining the molar mass, right? To find the mole to mole ratio. So those are two calculations that we're going to kind of oscillate between. All right. So let's do an example. Let's say we have a sample that contains carbon and hydrogen, and it contains 1.71 grams of carbon, and it contains 0.287 grams of hydrogen. Right?
Wait, that is 1.71 or 9?
7.
Gotcha.
All right. So those are the masses of my elements. And what I want to know now is what's the ratio, right, between carbon and hydrogen? So that's what I'm going to try to calculate. I'm abbreviating between as BWN. That's my little abbreviation for that. Right. What's my ratio between carbon and hydrogen, or basically what is the empirical formula? That's what that is. The ratio between the atoms, the little subscripts, that's going to give you the empirical formula, right? So the way I calculate that is very simple. It's taking the given mass in a case like this divided by the atomic mass. All right. So for carbon, the given mass is 1.71 grams. The atomic mass is 12.01 grams per mole. Very important to keep those units. So that we'll know what to cancel and what we're left with. All right. So what about what will we do for hydrogen? What's the given mass for hydrogen?
0.287.
Yep. 0.287. And what's the atomic mass?
1.008.
And that's in grams per mole. All right. And now all we have to do is calculate those numbers, right? So can somebody do the first calculation and then somebody do the second one? Anybody
I
got?
think the second one I got basically the same thing as the top, 0.2847. Let me make sure that's somewhat accurate or correct. Oh, well, yeah, because it's one, so
Okay.
yeah.
And what about the second one? What about the first calculation? Anybody got that one?
20.5.
20 more. Did you multiply?
Yes.
You did. You're supposed to divide.
Okay, I tried again.
1.71 divided by 12.01. What you got? Should be a fraction, a decimal, and not a whole number.
0.142.
All right, we'll take it. We'll take it. And this is moles now because this is grams and this is grams per mole. So this is the answer is going to be in moles. And that's what we want. We want to find the mole to mole ratio. Right. So the way we set this up, it's actually pretty simple. We're going to take C and we're going to write in that decimal 0.142. And then H, we're going to write 0.2847. All right. Everybody okay with that? So this is the moles that we calculated from the mass. Right. So now what we need to do to finish this is the smaller number of moles. We're going to divide both. Let me change the color on that so I can put a note in about and say what we're doing. We're going to divide both by that. All right, so divide by the smaller number of moles. What do you got for the first one? Anybody? It's just C1, is that right? But we don't have to show the one. Yes or no?
Yes.
Mhm. What about the second one? Is it H2?
Yes.
Okay, good. So this is the empirical formula. This is not the molecular formula. So we don't know the total formula. There's a way to calculate that we're going to do later, but not right this second. But right now, this is like what is the empirical formula? Remember we did this on the last exam. What does it tell you?
It's reduced.
It's the reduced form. So it just gives you an approximation of the atoms that are present, but it doesn't tell you the exact number, right? So this is the reduced form of the molecular formula. Right? It's an approximation. It's a relative. This is the relative amount of carbon and hydrogen. That's what the empirical formula tells us. Right? And one way to calculate it is to, again, find the mole to mole ratio based on a given mass and use that given mass of each element and find the moles based on the given mass and the atomic mass. So the given mass is going to be in grams and the atomic mass is going to be in grams per mole. Right? So that's one way to calculate empirical. There are other ways too, but this is one way to calculate it. All right, let's do another example just like this. I'm gonna pause for a second. I'm gonna see if you can work through another example. I'm not gonna break y'all out. I'm just gonna put the numbers on the screen and ask you to help me through it. So let's say we have a sample with 5.31 grams of chlorine and then 8.4 grams of oxygen, right? How do we set this up? So we have these two numbers are what? If we're looking at following the same example as the same format as the first example, what are these two numbers?
Your given mass.
These are the given masses. Excellent. And in order to calculate the empirical formula, we take what? And if we have a given mass, what do we need now?
Your atomic mass.
The atomic mass for each atom. So how would we set up chlorine? Let's set that up. Given mass is what?
He's on lunch.
It's 5.
It's early. Yikes.
5.31 grams. And then what's my atomic mass of chlorine? And then you just get that number straight from the periodic table.
$35.453 grams per mole.
Okay, so we're gonna say 35.45 grams per mole. Excellent. All right. And then what about the oxygen?
8.40 over 16.
And this is grams and grams per mole. It's very important to keep those units. Otherwise, everything is going to get lost in the sauce because what we're trying to find is the number of moles of each one of the components, right? So what do we get for chlorine? Anybody got that? Calculating that?
$0.149.
49. Let's go ahead and round that up to 0.15.
Right.
All right. And what about the oxygen?
Scroll back over so I can see. It's 1.34.
Say that again.
1.34.
8.4 divided by 16. It should be a
8
fraction. The bottom number is bigger than the top number.
divided by 16. Oh yeah, you're right. 1.0.525.
All right, 525. And this is moles. Let's keep the units because we don't want to get confused. So again, we're trying to calculate the empirical formula. So that means we want the number of moles of each element that makes up this compound. And then now we know that, right? So we're going to write this out. So chlorine is 0.15, and I'm just going to say 150. And then oxygen is 0.525. Now what do we do? What's the next step?
Divide both sides by the smaller one.
Smaller one. So we're going to divide this by 0.150. That's going to cancel. And we're going to divide this by 0.150. All right, what do we get from that? I'm just going to write, I'm going to put the one in. You know that the one is not supposed to be there, but I'm going to put it in just for clarity for now. Well, not, but it's not going to be one. Actually. All right, go ahead. What about oxygen? What do you get? 0.522 divided by, not 0.015, my bad, 0.15, 0.150.
I had 3.5.
Yep, good, 3.5. All right, now we got a problem, right? Because, go ahead, Saxton.
I wasn't sure why we're doing that as a final step.
Because we're trying to write the empirical formula. So we need to write out the empirical formula is going to show you the relative ratios of all the atoms.
Okay. So
So-
basically like the simplest.
So one of the steps is to find the moles and then plug those numbers of moles into the formula like this, and then divide by the smallest number of moles. Divide each one by the smallest number of moles. So that leaves us here. But this is not good because we can't have a fractional subscript. So remember when we were doing multiple proportions, and if we got a weird number, we can make it a whole number by just multiplying it by some number to make it whole. We can do the same thing here. So we're going to take this whole thing and we're going to put a 2 out here and multiply each subscript by 2. Right? So the empirical formula in this case is going to be Cl2O7. And I'll put a note in here.
I was just about to say, hold on, because I was writing.
I'm not, well, I'll scroll back out. Right, so we did this same thing when we were working on the law of multiple proportions, right? Where we would come up with some fractional ratio, 2.5 over 1, and then we multiply the top and the bottom by 2 to get 5 over 2. That was on the test. That was a test question. It's the same idea, right? You have a fractional subscript. You have to make it whole. Right, you can't leave it like that. So we'll just multiply everything by 2. That takes the 3.5 up to 7, and it takes the chlorine up to 2. So this is the empirical formula for a sample that contains chlorine and oxygen in this amount, in this ratio, 5.3 grams to 8.4 grams. The empirical formula is Cl2O7. All right, any questions about that? It's the same setup as the previous problem. The only added step here is that we had a fractional subscript, so we had to fix that. So we just multiplied everything by 2. Right, because you'll notice that you'll never see a fractional subscript in a chemical, in a molecular formula, ever. Everything has to be a whole number, because remember, the law of multiple proportions says that when atoms combine to form different compounds, they combine in small whole number ratios. Right, that's the basis of all of that. All right, any questions about anything we've done so far? Right, so now I can pull this chart up that I've been moving for 2 days. All right, but this is kind of a flow chart as to how to approach these problems. So you have, again, the mass of your atoms. Let me zoom in on that. And you divide by the molar mass to get the moles of your atoms. Then you divide by the lowest number of moles to get the mole ratio. And then you convert to the lowest whole numbers, which normally you won't have to do anything else. But in this case, we ended up with a fraction. So that's where that conversion part comes from. If there's no fractions, then you don't have to worry about that part, because what's left is going to be your empirical formula. All right. Questions? Any questions? All right. I want you to work on this over the weekend. Just play with it. We got a sample. I want to put on your own up here. That contains 0.130 grams of nitrogen and 0.320 grams of oxygen. What is the empirical formula? All right. You can work on that over the weekend, and on Monday, somebody can volunteer their answer. All right, so we're going to stop here. Let me stop recording.